Invertible functions. In this module, you will learn how to identify invertible functions. Recall that a function is a relation in which each input is related to exactly one output. Suppose we have a function f that maps a set x to a set y. If an element A in set X maps to an element 1 in set Y, then we say f of A equals 1. Now let's define an identity function. We denote this function by I, and if it operates on some set, say X, then it maps the set X to the set X itself. The interesting property of this function is that it maps each input back to itself. If A is any element belonging to set X, then the identity function of A is A itself. We will use this information to identify invertible functions. A function is invertible if it has its inverse. First, let's understand with the help of an example what the inverse of a function is. Suppose we have a function f that maps a set x to a set y. We can see that A is associated with 1, B is associated with 2, and C is associated with 3. If there exists a function that maps a set y to a set x, such that 1 is associated with A, 2 is associated with B, and 3 is associated with C, then this reverse function is called the inverse of f. It is represented by f with -1 in superscript and is read as f inverse. Now if we apply input A to f, we get the output as 1. When we apply this 1 as an input to f inverse, we get the output A, which is equal to the input applied to f. If we repeat this procedure for the remaining elements in the domain of f, we get the output of f inverse, same as the input applied to f. So we see that the composition of f inverse with f is an identity element on set X. Let's see what happens when we apply an input to f inverse and its output to f. If we apply input 1 to f inverse, we get the output as A. When we apply this A as input to f, we get the output as 1, which is equal to the input applied to f inverse. If we repeat this procedure for the remaining elements in the domain of f inverse, we get the output of f, same as the input applied to f inverse. So we see that the composition of f with f inverse is an identity element on set Y. Using this discussion, we can say that a function f that maps x to y is invertible if there exists a function g from y to x such that the composition of g with f equals the identity function on x, and the composition of f with g equals the identity function on y. Also, the function g is called the inverse of f. Now let's see how we use this fact to identify invertible functions. Suppose we are given a function f so that f of x equals 4x plus 3. We need to show that it is invertible. Also, we need to find the inverse of f. Let us assume that y is any arbitrary element in the range of f. Then y equals 4x plus 3 for some x in the domain of f. Now solve the equation for x to make y an independent variable. We get x equals y minus 3 whole upon 4. Note that y becomes the input and x becomes the output in this equation. So, use this equation to define a function g that maps y to n so that g of y equals y minus 3 whole upon 4. Now find the composition of f and g. Substitute 4x plus 3 for f of x. Now substitute 4x plus 3 wherever there is y in g of y. We get x, which equals identity element on set n. Now find the composition of g and f. Substitute y minus 3 whole upon 4 for g of y. Now substitute y minus 3 whole upon 4 wherever there is x in f of x. We get y, which equals the identity element on set y. This shows that f is invertible and g is the inverse of f. The inverse of every function is not a function. Let's look at an example. Suppose we are given a function f so that f of x equals x square. We need to check if it is invertible. Let us assume that y is an arbitrary element in the range of f. Then y equals x square for some x in the domain of f. Now solve the equation for x to make y an independent variable. We get square root of x square equal to square root of y. Since the power of x is even, its square root is x. Since the power of y is odd, it has 2 square roots, one positive and one negative. We cannot use this equation to define a reverse function g because a function cannot have 2 outputs for the same input. Thus, the given function is not invertible. In this module, you have learned a function f that maps x to y is invertible if there exists a function g from y to x such that the composition of g with f equals the identity function on x and the composition of f with g equals the identity function on y. Also, the function g is called the inverse of f and is denoted by f with -1 in superscript.